Hi everybody. So this is sort of the review. This is the additional exercises for forces and free body diagrams for CP Physics. So let's get into it. A1, what is the minimal force a mother must exert to lift her 5 kilogram baby out of the crib? Well, if you remember, free body diagram is usually a good place to start with anything. We got a 5 kilogram baby, which if you remember, Fg equals mg. We've got the force of gravity, which equals the mass, which is 5, times the pull of gravity, which is -10. So going down, we've got an Fg of -10 newtons, which means in order to lift the baby up, we need to pull with more than 10 newtons. I think I have that wrong. Uh, the data reads the bigger number, right? So we have to pull with at least 10 newtons, so the force must be greater than 10 newtons to pull the baby up. Next, on the moon, gravity is 1/6 out of the Earth, while on the moon, Buzz Aldrin carried his back on his back a support system that would weigh over 1,760 newtons on Earth. What did his backpack weigh on the moon, and what was his mass on the moon? Well, I think the easy way to start this is to figure out what the mass is, because mass doesn't change. So on Earth, it's mg equals fg, and the mass is what we're sort of looking for. So let's see, equals 1760 newtons equals something, the mass, times 10. So the mass of this backpack was 176 kilograms. And the mass doesn't change. So on the moon, on Earth, on Jupiter, near the sun, it's always 176 kilograms. So then we can look at what it does on the moon. And if you remember, mg equals fg. Well, if we change where we are, we're changing g. So the mass on the Earth, or I'm sorry, on the moon doesn't change. So we're still dealing with 176 kilograms, but we're going to change it to the moon's gravity, which 1/6 of 10. Last time I checked, as I have my calculator here, 110 divided by 6 is 1.666667, 1 2/3. So 1.667 equals the new gravitational force, which is 293 newtons, much lighter on the moon. Next, common malady in runners who run too hard on the surface is shin splints. If you've ever had them, you know it's not pleasant. For runners, 7 kilogram leg hits the pavement so that it comes to rest with acceleration -200 meters per second squared on each hit. How hard must the what kind of force must the runner's leg withstand? That's F net equals ma. So we're looking for the force. They give us the mass. They give us the acceleration. So F net equals mass, which is 7, times acceleration -200. Which equals an F net of 1,400 newtons, -1,400 newtons, which is actually a pretty big force. Next up, district soccer championship finals. Elizabeth kicks a 0.6 kilogram soccer ball with a force of 80 newtons. How much does the accelerate? So we are given a force, we are given a mass, we are given an acceleration, so we can figure all this stuff out, I hope. 80 newtons equals 0.6 times A. And if we divide both sides by 0.6, divide by 0.6, divide by 0.6, goes away. Acceleration is going to be 133 1/3 meters per second squared. Sarah, we're going to skip number 5 and move on to number 6. Sarah, whose mass is 40 kilograms, is on her way to school after a winter storm when she accidentally slips on a patch of ice whose coefficient of sliding friction is 0.06. When the force of friction what force of friction will eventually bring her to stop? So we're looking for the FF, and we're actually dealing with sliding friction, so it's K, FFK, kinetic friction. If we remember, that equals mu times the normal force. We are told that she has a mass of 40, so the normal force is essentially mg, because if we remember, you got Fg going down and Fn going up, so the Fg going down is 40 times 10, negative, and the normal force going up is 40 times, so that'll equal 400. 400. So if it's 400 newtons going down, it'll be 400 newtons going up. So now we know our normal force. So Ff equals mu times Fn. But again, we know our normal force because we just figured it out. Normal force is 400. And the mu, they actually tell us, is something very, very small because we're dealing with ice, 0.06. So whatever 0.06 times 400 is, should be a force of friction, kinetic, of 24 newtons. Hope that helped. These are really just plug and chug if you understand the theory. In her physics lab, Molly puts a 1 kilogram mass on a 2 kilogram block of wood. It's almost like you did this in lab. She pulls a combination across another wooden board with a constant speed to determine the coefficient of sliding friction between the two surfaces. If she pulls with a force of 6 newtons, what coefficient of friction is there? So we're calculating mu. Again, Ff equals mu times the normal force. We know she's pulling it with 6 newtons. So let's draw a free body diagram real quick. The forces we have are gravity, normal. She's pulling it with applied force, and we are dealing with friction going the other way. Kinetic, the flavor is kinetic friction. And there is no acceleration. She's constant speed, so we know all 4 of these are going to balance each other out. We know the gravitational force is 1 kilogram plus 2 kilograms, which is 3 kilograms times the acceleration due to gravity, which is negative 10. So that'll be negative 30 newtons going down. Therefore, the normal force must be positive 30 newtons going up. She's also pulling with a force of 6 newtons going to the right. That means friction must be 6 newtons to the left, so we'll give that a negative 6 newtons. So the force of friction is 6 newtons, which equals mu times the normal force, which is 30 newtons. And remember that we're starting to deal with vectors here. So yes, technically it's negative 6 newtons, technically it's positive 30 newtons, so we should get a negative mu, but we kind of say because it's pulling one way or the other, we can kind of disregard the positive or negative now. So last time I checked, we're going to have to divide both sides by 30. Don't get caught in the trap of dividing both sides by 6. We're going to divide both sides by 30. And mu is going to end up being a very small number. 6 divided by 30, mu will be 0.2. And there is no unit for mu. Okay? So then we move, undo add page. Don't want a new page. Alright, so I hope that helped. Going on, we are skipping number 8 and moving directly to number 9. Irma receives a 5 kilogram package in the mail tied with string that goes around each. We have 4 pieces of string sort of here. Irma lists the box by the string in the center so that each piece of string makes a 45-degree angle with the vertical. What's the tension on each piece of string? So this is kind of interesting. Each of these is generating up. Each of these strings, and I'm going to sort of draw that over here. So the string is going like this, but the force, I'm actually going to go for a classy arrow here just to make things kind of straighter. So we've got the string is going like this, but it's generating a force going straight up. Okay? And the cool part about this is something we already know. You know, the hypotenuse of any triangle is going to be bigger than any of the legs. So the interesting part is how big that leg is. And you might ask me how. And I would answer to you, well, you know that there are 4 of these strings. So there's one over here, there's one over here, there's one over there, and then there's one in the back. So we know there are 4 of these strings, and each of these strings is all generating an upward force. So, you know, for what it's worth, we've got this 5 kilogram package going down. So we got the weight force, Fg, of 5 kilograms, which is negative 50 newtons. So we know that there's negative 50 newtons going down. And we've got these 4 strings that are each generating something going up, and I don't want to do this with not straight lines. So we've got an upward force from one string, we've got an upward force of another string, and we have an upward force from the third string, and we got an upward force from the fourth string. So there are 4 strings that are each equally carrying that 50 newtons. And if you divide that 50 newtons by 4, you should get each of these strings is generating an upward force of 12.5 newtons. And in my class, if you remember, I did that thing where I had that string across and we hung that mass on it, and all of a sudden the string kind of drooped. And I said, if you pull this way and you pull this way, you still have to have an upward force to counteract the gravitational force from that string. Well, this is sort of the same thing that's going on. And when you're talking about a package or anything like that that's being supported by multiple strings, each of those strings is carrying a quarter of the load if it's 4 strings, or if it was 3 strings, each of those strings would be carrying a third of the load. Now, if you look at this, all of these forces, paper cutter, each of these strings is pulling, or each of these forces is straight up, but the string doesn't pull straight up, it pulls at an angle, and they actually tell us what that angle is. It is 45 degrees to the horizontal. So we've got an upward force of 12.5 newtons, 12.5 newtons, 12.5 newtons, and we've got an angle of 45 degrees, and we're looking for the hypotenuse of the angle, because the hypotenuse is what the string actually is, this tension. Okay? And I see they've got 45 degrees to the horizontal there, but if you remember anything about alternate interior angles, they're saying this is 45 degrees. Well, according to geometry, so is that. And if these two are parallel lines, which they are because they're both vertical, and you've got some line here that crosses both of them, the interior sides that are alternate are the same angle. So this guy's 45, this must be 45. You probably don't remember that from geometry, but I do. So there you go. Mr. Harris, the guy with the crazy circle, he taught me something. Anyway, so let's see what we can do with this. We've got we're looking for the hypotenuse. We've got an angle, and this is the side that's touching it. This would be the side down here that is the opposite, but we don't really care about it. So we've got an adjacent side to the angle, and we're looking for the hypotenuse. And last time I checked, we would be using cosine for that. So cosine of 45 degrees equals the adjacent over the hypotenuse. But we know what the adjacent side is. The adjacent side is 12.5. And we're trying to figure out the hypotenuse, so you have to cross multiply. H cosine 45 equals 12.5, because we multiply both sides by h. And these cross out, so we have h cosine 45, then we have to divide both sides by cosine 45. Those cancel out, so we're left with h equals 12.5 over cosine 45, which should be a hypotenuse of 17.68 newtons. So that is the hypotenuse. And if you remember, sort of the demonstration that I gave you in class was, look, you can have something really light, but the bigger that angle is, the flatter that line gets, the more tension there is. And this is actually a case in point. Look, I only need to generate 12.5 newtons of upwards force here. But the second I introduce this angle, I need more force in the line, more tension in that string. And that's why, to generate 12.5 newtons of force, I have to come up with 17.68 newtons of tension. So this is something that we did in class, not exactly with a box and 4 strings, but it was sort of a demonstration that I was trying to show you that, as you introduce angles into what we call statics, when these things are all stationary and the forces are balanced, if you look at this, 50 newtons down, 50 newtons up, we end up playing with angles, and in order to keep everything balanced, we have to, the bigger the angle gets, the more, the bigger this hypotenuse becomes, the more force we need in there. So I hope this kind of makes sense. This is a good question to just show you sort of what's going on and how important our trigonometry is in physics, and specifically in this sort of physics. So, and this is another sort of case in point of what's going on, but the beauty with this one is there's no angles. So to make extra money during the summer, Mr. Garber, a 66-kilogram physics teacher, paints the outside of houses while sitting on a 4-kilogram plank, suspended by 2 vertical cables. So, and then the question is, what's the tension in each of the 2 cables? Okay, so the 2 cables are vertical. So let's make a vertical cable. Oh boy, vertical the wrong way. Vertical cable up, and he's suspended on a plank. Oh wow, they actually kind of connect. Good. So, and let me be Picasso here. Here's Mr. Gerber, somehow levitating. There we go. It's going to actually touch there. So he's got a mass of 66 kgs, and the plank has a mass of 4 kgs. So how many kgs do they have together? Well, 66 plus 4 is 70 kgs. And I guess we can go for a free body diagram now. We know that 70 kgs is going to turn into an FG of 700 newtons. And if there's 700 newtons going down, there have to be 700 newtons going up, unless Mr. Gerber wants to fall down, and we don't want him to do that because that would be a bad day for Mr. Gerber. So we're going to have to come up with 700 newtons going up. But there are two strings, 2 cables, and they're both vertical. So if there's 2 cables, each of them can carry a load of exactly how many newtons? And I hope you guys in your infinite wisdom are intelligent enough to tell me that each of those must have a tension force of 350 newtons. So 350 from that side, FT, 350 from that side. So each of these is 350 to counteract the 700 newtons going down. Next, while camping in Denali National Park in Alaska, a wise camper hangs his pack of food from the rope tied between 2 trees. Why would you want to do that? Because if you put food on the ground, things will eat it. If you put it between 2 trees, fewer things will eat it. Anyway, keep food away from the bears. If the 5-kilogram bag of food hangs from the center of the rope that is 3 meters long and the rope sags 6 centimeters in the middle, what's the tension of the rope? This is difficult. And it sort of begs the question. I'm just going to draw. I'm going to draw. So we got 2 trees. 2 trees. And we've got this rope, which is 3 meters on this side and 3 meters on this side. And there is a 5-kilogram sack of food in the middle. And we know that meters. And we know that this thing sags by 0.06 meters. Why is it 0.06? Because it is 6 centimeters. So, I'm sorry, the rope is not 3 meters long. The rope is, oh wow, from the center of a rope that is 3 meters long. So each of these sides, I apologize, must be 1.5 meters, which now has screwed up all of my calculations. So I'm going to have to do this with you. We're doing real physics here, folks. 1.5 meters. 1.5 meters. Sorry, that's what happens when I don't read very carefully. So, each of these is 1.5 meters. Each side of this is 1.5 meters long. And we're dealing with this 5-kilogram bag of food. So, one thing you guys should probably realize is these really shouldn't be on the same triangle. And what I mean by that is we've got a mass and then we've got displacements. So, you know, these aren't the VIVF ATD things that we've been dealing with otherwise, which you'll see on the quiz on Friday. These are more sort of logic questions. So, let's sort of break this up into 2 separate scenarios. And what I want you to emphasize, or what I want you to try and figure out, is the angle here. Because believe it or not, there is only one rope. There is only one scenario here, and we can think about them as distance triangles and maybe force triangles, but they are the same triangle. So if we can figure out the angle for the distances, we have the angle for the forces, and if we have the angle for the forces, we can start doing some other cool, F net equals 0 stuff, because all of this is stationary. So if you can sort of step out of your comfort zone and understand that, this will work a little bit better. So I'm going to make a displacement triangle. I'm going to take this side right here. So, and this is not to scale, 0.06 meters. And then there's my tree. And I know that the rope is 1.5 meters long. And if I can figure out what this angle is, well, then I can sort of do something kind of cool here, where I've got a weight force that is 50 newtons, and I need to figure out what's going on with two ropes. Tension, tension, T, T, and if it's 50 newtons going down, this rope is responsible for 25 newtons going up, and this one is responsible for 25 newtons going up. But I don't care about the up, I care about the tension. But if I have a magnitude here, I can almost make a triangle, figure out that angle, and if I know this angle, it's the same as that angle. And if I know that side's 25 and I have an angle, I can figure out the hypotenuse. That's the logic here. This is a stretch. We haven't talked explicitly about this, but it's the same theory that we've been really dealing with. These are statics. Everything is going to cancel out. The F net's 0, and this is sort of what's going on. So to start off, I've got a hypotenuse on this side of 1.5 meters and a vertical of 0.06 meters. And I'm looking for this angle. So this side would be the hypotenuse, and from this angle, this side would be my opposite side, and O and H, I'd be looking at sine. And if you remember anything about trig from a long time ago, if you take the inverse sine, you can figure out the angle. So inverse sine of theta, which we don't know, equals the opposite, 0.06, over the hypotenuse, 1.5. And let's see here, second sine 0.06 divided by 1.5. That angle is 2.29 degrees. I'm going to round it to 2.3 degrees. 2.3 degrees. Okay? And if that's 2.3 degrees, then this thing is 2.3 degrees. So now, I'm going to do this. We're going to make ourselves a big old triangle here that is now, I'm done with this, 25 newtons up. This goes like this, that's my tension. And this is 2.3 degrees. So the question is, if I have this, that's 25 newtons, how big is this? If this is 23 degrees. Well, again, here's the angle I know. We can finish out the triangle, although it's not really necessary. 2.3 degrees. So I've got this as an opposite, this as my hypotenuse. Again, I'm going to use sine. Sine of 2.3 degrees equals the opposite side, 25 newtons, over the hypotenuse, which is my tension. Now the crazy thing is, this is the x side, and that's my adjacent side, not that it matters, but this tension pulls to the right just as hard as the other tension, if we drew it in, pulls to the left. So the two tensions, well, the two horizontal components of the tension cancel each other out. And what you're left with is two 25s pulling up and 150 pulling down, and that would give you an F net of 0, which means our food doesn't fall to the bears. Anyway, so finishing out and figuring out what the tension is the only thing we have to do. Multiply both sides by H. Those H's go away. Now I've got H sine 2.3 equals 25. I'm going to divide both sides by sine of 2.3. So those go away, and I'm left with H equals 25 over sine of 2.3. And sine of 2.3 is actually a really small number. So 25 divided by sine 2.3, we actually get a hypotenuse, are you ready for this, of 622 newtons. Can you imagine that? You're hanging something that weighs 50 newtons. And in order for you to support that with such a small angle up here, again, this is what we did in class. In order to support that, you have to kick in 622 newtons of force just on this line. And you need another 622 newtons on this line to hold your sack of food that has a weight of 50 newtons. Isn't that crazy? So you almost need like 1,200 newtons of force here to hold up 50 newtons. I think that's interesting. You probably don't, but I do. So I hope that makes sense. This is like the nth degree. I'm not going to ask you this explicitly on the quiz on Friday, but I think it's a good exercise in logic to sort of see if you really understand what's going on with the statics. Okay. The next thing, the last question for you. In the figure, a 1,240 kilogram wrecking ball is pulled backwards with a horizontal force of 5,480 newtons before being swung against the side of a building. Bad day for the building. What angle does the wrecking ball make with the vertical when it's pulled back, and what's the tension of the ball supporting cable when we actually do this? So we're looking for this angle, and we're looking for that F. All right, so this shouldn't be too complicated, I hope. Let's sort of think about this logically, and to do it, I'm actually going to make a free body diagram. At this particular moment, the cannonball, or the ball, not the cannonball, the wrecking ball, is stationary, which means all of the forces have to cancel out. So we know, I'll get a straight line here, we know that there's a force going down, and that is a big force. It's a 1,240 kilogram wrecking ball. So Fg of 1,240 kilograms must be 12,400 newtons negative. Which, interestingly enough, why is that there? What did I do? Sorry, guys. Go away. Which, interestingly enough, has to be offset by this other force. So, and they actually do this. They'll have a couple of rings. There are a couple of strings pulling the cannonball. So I've got a string pulling the cannonball this way with a force of 5,480 newtons. 5,480, and it's actually my applied force. And you can actually see this. They'll actually pull it one way with a string and then let it go, and then the cannonball goes the other way. And all of this is done because there is a wire going this way. Okay? Now, the interesting thing is this wire has to balance out the 5,480 from the applied force and the 12,400 from gravity. And this just got really easy because this wire is pulling, and we did this in class, sort of, this way with, if this is positive 5,480, the wire has to be pulling this way with negative 5,480. And it's also got to be pulling up. If gravity's pulling it down with 12,400 newtons, this thing has to be pulling up with positive 12,400 newtons. Now, I'm sorry, that's kind of dirty. Positive 1, 2, 4. Yeah, that doesn't look like a 9 anymore. But remember, these aren't real forces. The actual force is the tension force. And I've always tried to do these in different colors in class. You know, the free body diagram is this, the black stuff. The components of the black stuff are the red stuff. So if we wanted to, we could do an XY chart. I don't think it's necessary, but if you want to, be my guest. And you would have, and I'll start it off for you at least. You got the XY, you got the tension, Ft, you've got gravity, and you have the applied force, and you know that total these things are going to be equal to 0. So the Fg, you know, is 0 in the X, the applied force is 0 in the Y, the gravity is negative 12,400 in the Y, the applied force is 5,480 in the X, and then this stuff has to be negative 5,480, which we've got there, and positive 12,400, which we have here, to make something out of tension. So they ask us, well, don't make me a free body diagram. We have it. What they want to know is the angle, and they want to know how big the tension is. So I guess to start, the easy way to do it is going to be to look at the angle. This is the angle we're looking at because that's theta, and that's what we got. The angle we're looking at here, compared to this angle, this is my opposite side, and this is my adjacent side. So remember, if we're looking for sides, we go forwards with our trig functions. If we're looking for angles, we have to go backwards with our trig functions. So an O and an A, I would personally use tangent. And not just any tangent, but the inverse tangent, because the inverse tangent gives us the angle. So the inverse tangent of opposite over adjacent, negative 5480. You don't even need the negative. In fact, I'm going to drop it just to make my life a little bit easier. The inverse tangent of 5480. I can't write nicely. 5480 over 12,400 should give us, and I'm going to confirm this, inverse tan 5480 over 12,400. The angle is 23.84 degrees. Okay, so yeah, when you do this, inverse tan of the fraction gives you theta. All right, so that's like the whole what we're doing there. And then the other thing they want to know is what's the force of tension. Well, I have an a squared and I have a b squared. I could probably figure out the c squared, and I hope you guys can figure that out to be 13,524 newtons. I hope this one makes some sense. Why? I hope this one actually makes some sense. Again, I don't know if I'm going to ask you explicitly this on the quiz, but it's a good thought process logic problem. 13, 14, 15, and 16, I told you not to worry about because they're dealing with pressure. So there you go. I hope at least the front of this thing makes some sense, and if not the back, I would look at what we did on Tuesday and during class on Wednesday with those 4 problems also when we actually get into things that are accelerating. And you should be good to go for the quiz, okay? I would look at all the problems that we've been working with over the past few days. Hope this helped. Now to figure out how to stop recording.